Okay, let's do part 1 of lab 10, the op-amps imperfection lab. Okay, so in this lab exercise we're using the op-amp integrator, and remember the integrator has V out is minus 1 over RC integral dt V in of t, and the way you derive that is, well, okay, so normally this is our input. Our input is usually, our input is grounded in this drawing. I guess I can momentarily unground it. So then you say, okay, this current must be the current flowing to the right through this resistor R. So if this is grounded, then the golden rules say feedback will try to keep this grounded. So then this current is just V in divided by R. And then that same current flows through the capacitor. And when the current flows through that way, then this end will be more positive and this end will be more negative. And this stays at ground, so that makes V out negative. So, right, remember we have for a capacitor I equals C dV by dt. It's just a time derivative of Q equals CV. You take the time derivative of both sides. So that again, right, so that gives us, well, I guess we could just work it out, alright. So here, I is V in over R. Yeah, there you go. So then you get, and this is V out, and then there's also a minus sign because the voltage across the capacitor, if this end is 0, you're increasing this side. So anyway, you get a minus sign because V out is becoming more negative if you're fixing this at ground and you're pushing current in this way. So there's actually a minus sign here. So then that gave us dV out dt equals, okay, right, minus V in over RC, right, you can integrate both sides, and there you go. You get V out is minus 1 over RC integral V in of t dt. Okay, but we digress. So if we fix V in always at 0 by grounding this input here, then in the golden rules picture, the output should be 0, or at least it should be constant, because we're integrating 0 with respect to time. But what we're going to see in just a minute is that, in fact, within a few seconds, the output wanders off to the plus or minus power supply voltage. And you say, why is that? Well, there are two effects. We want to try to figure out which effect. Well, I guess we want to try to quantify the two effects. There are two main effects, okay? So one is that there's this current called I bias. So I bias, and it's because this op-amp is, the inputs of this 741 op-amp are the base electrodes of bipolar junction transistors. And so in order for those transistors to be on, the base has to draw a little bit of current, kind of in the, I don't know, microamp or fraction of a microamp range. So actually, well, actually that's a little bit of an exaggeration because this is going to be kind of tens of nanoamps. So we have I bias for these 741s is, well, the typical value for the batch of chips that we have here is about 20 nanoamps, but the data sheet I think says typical value is closer to 100, but anyway, for our sample batch it's more like 20 nanoamps. So that's one thing. So it's not going to make any difference flowing into this non-inverting input, which is just coming from ground, but flowing in through here, you see it has the same effect. I mean, it's basically this current will effectively charge up the capacitor. You say, well, actually, you could say, why is that true? Well, you could say, well, that current flows across this resistor. Yeah. So then you have I bias times R looks just like an input voltage. Okay, so here this voltage is 0, even if there's a current flowing, but this voltage, instead of being 0, is going to look like I bias times R, because there's this bias current flowing. And then the other thing that will happen is we have this thing called V offset, which says that feedback tries to make the two inputs equal each other, but the op-amp, due to little imperfections, when it thinks they're equal, they're actually different by some tiny amount that we're calling V offset. And the easiest way to model that is to pretend, it's actually inside the op-amp, but you want to pretend that there's a tiny little battery here. And this is V offset, and we have V offset is like a few millivolts, and we don't know what sign it is. Whoops. So it's like kind of a few, it's on the order of a few millivolts. Okay, and so then we'll try to quantify in a moment how big those two effects are. But basically we have like as if V in were I bias R, and then we have as if V in were V offset. As a matter of fact, I guess then you could say here, so dV out dt. So let's take these two effects, and let's say we don't know what the signs are. So we have actually we do know what the sign of this one is, but anyway, I bias R over RC, so the R will cancel. Okay, so then this will be like 20 nanoamps over 1 microfarad. Okay, so we'll work out what that is in a second. And then there's another term which is, it's plus, we don't know if it's plus or minus, but anyway, V offset over RC, and we'll say that's going to be something like a few millivolts over, okay, and then RC, kilo ohm times a microfarad is a millisecond, 1 millisecond. So this is like a few volts per second. And let's see, nanoamps divided by microfarads. So this is actually kind of like 0.02 microamps per microfarad. So that's like 0.02. Okay, so actually this is kind of like 0.02 volts per second. If I did that right, right? 20 nano is like 0.02 micro. Yeah, so it seems like this effect is going to be a lot smaller. So the effect of I bias will be pretty tiny. I think it's like 0.0, like maybe less than 1/10 of a volt per second. But the effect of V offset should be pretty big. It should be like a few volts per second. So I guess what we expect to see is a slope in. So we have no input. I mean not no input, but we have like a grounded input. So we think that it should be integrating 0, so it should be constant. But because of these two effects, and it seems to be dominated by this one, we will see this capacitor charge up, so we'll see V out move with a slope of kind of a few volts per second, and it will stop when it reaches one or the other power supply rail. And then how do we set the initial conditions so we can start integrating? We've wired up a little push button switch here. So then when we close the switch, it zeroes, it removes the charge from this capacitor, and then we'll open the switch and we'll start the integration. So we're going to see that happen right now. Okay, let's go around and see what we have built here. So we have this 1K resistor going from our input. Our input's just connected to ground, but we have our grounded input going through this 1K resistor to the inverting input of the op-amp, which is pin 2. So here we go. Here's pin 2, the inverting input of the op-amp. Pin 1 of the op-amp is not connected to anything right now. It's normally not connected to anything. Then pin 2 will also be involved in the feedback loop, so we'll keep that, bear that in mind. Okay, then pin 3, the non-inverting input of the op-amp, is grounded. Okay, so that's this little black wire connecting it to ground. And then pin 4 of the op amp is our negative power supply voltage. That's connected to minus 9 volts here on the EE board. And then pin 5 is normally not connected to anything, although we'll use it a little later. And then pin 6 is the op amp output here, or up here. So it's connected to one end of this capacitor. So this blue capacitor you see here, so it's actually pin 6, the left end of this capacitor goes to pin 6. And then this green wire here is going to scope channel 1, the yellow scope channel. And then, okay, this potentiometer over on the right, you're going to ignore that for now. This is what we're going to use to trim the value of V offset in a moment. But so you don't know about that just yet, so pretend that's not there. Then it was kind of tricky to fit this capacitor in, so the right hand side of this capacitor is actually one row to the right of the right side of the op amp. And then I have this little blue wire is going back to pin 2. So basically here's this end of the capacitor, and then the other end of the capacitor is going back through a little wire over to pin 2 here. So that's the inverting input. And then I wanted a switch. You could just use a piece of wire for this, but it's kind of convenient to have a push button switch. And Joe's actually kindly provided us with a bunch of push button switches. So I have a push button switch. So I use 2 little wires here. One little wire goes to this side of this push button switch. This other little wire goes to this side. So the push button switch is connected across the capacitor. When I don't push anything, the capacitor can mind its own business. It's charging. But then when I push the button, it's like discharging the capacitor. And then I let go of the button and the capacitor stops discharging. So, and then you can kind of see what, I think that's all. Oh, and then I guess, right, pin 7 now is connected to this little red wire up to my positive 9 volts. So my convention is I like to use this top red row for plus 9 volts, this bottom red row for minus 9 volts, and then this bottom blue row I use for ground. And I haven't found a use yet for this top blue row. Okay, so you can just barely see my scope in the top right corner of the screen. So see if you can see what happens when I push this little button. Here, let me try pushing it with I'll push it with the screwdriver. I'm going to push this little button to reset the capacitor. And I think, yeah, so you can see that the voltage on the capacitor goes to 0. That's the output voltage, goes to 0. And then watch how quickly it charges back up to, in full scale, you'll see it stops at about 8 volts, a little bit before the power supply voltage. You see, it actually only takes it a few seconds, basically, to get from 0 up to like 8 or 9 volts. And our prediction, remember, was like a few volts per second due to V offset. So that prediction was pretty good. So that's consistent with a V offset value of kind of a few millivolts. So if I really zoom out on the horizontal scale of the oscilloscope, then you can see now I have 1 second per division horizontally on the oscilloscope, and I have 2 volts per division vertically. So I'm holding down the little switch to zero out the capacitor, and then I will let go of it when it's halfway across the screen. There we go. I let go of it, and you can see that the slope appears to be, let's see if we can measure that. So that gives me 8 volts roughly in about 2.5 seconds, so that's about 3.2 volts per second for a slope. So that's consistent with about a 3 millivolt V offset. And by the way, it only gets up to about 8.5 volts, so it doesn't quite get up to the 9 volt power supply. And I think on the lower end, if it were to saturate down below instead of above, it would be even less close. I think it's like 7.5 volts. Okay, so then the next trick, this is actually, it takes a little while to puzzle this through, but if you look at the math I did on page 6, you can see me puzzle it through for you. you don't really have to puzzle it through yourself. But if we disconnect this, just let it float, okay, so it's as if we erase this resistor, then Ibias can still charge the capacitor, but there's no longer this V offset over RC term. There's just this Ibias over C, right? So this R doesn't matter because you can cancel it top and bottom. So it's as if you really erased this resistor. So then we'll just see this Ibias over C term, which I think is going to be a lot slower. Like, I think it's probably going to take tens of seconds to, it's going to take seconds, maybe tens of seconds to go even a volt when we do that. So, okay, without changing anything yet, let me just reset the capacitor one more time, and you can see we're still at this few volts per second slope. And then let me reach in, and I will just remove the little grounding wire for this resistor. So now it's not connected to anything. The resistor is just floating in the air. And now let's zero the capacitor again. And I think we're going to see a much, much slower rise. Yeah, look at that. So you can see it's very gradually going up. You can kind of see every time the raster scan goes by, it's going by a little higher than it was last time. But it's going to take us many seconds to go even 1 volt. So let me change the scale and get a measurement of that for you. Actually, see, this is so slow. You could do it with a stopwatch. Actually, in the lab I kind of recommend doing it with a stopwatch. So maybe what I'll do is I'll pause the camera and I'll do this with a stopwatch. We'll see how long it takes to go 2 volts. Okay, and then I'll report back to you. Yeah, so I saw that I got about 2 volts in about 80 seconds, about 1 minute and 20 seconds. So that's a 40th of a volt per second. So that's 25 millivolts per second. And then we can say, oh, hey, that's pretty interesting. Because here, if it were 20 nanoamps, that would give us 20 millivolts per second. So actually, I guess what we're saying is that this corresponds to Ibias about 25 nanoamps. Okay, so cool. So we effectively, we measured the slope the first time. It was some combination of V offset and Ibias causing that initial slope. We didn't know a priori which was which, but based on orders of magnitude, we thought it was probably dominated by V offset. So, assuming that it was dominated by V offset just for the moment, then we inferred a value of V offset of a few millivolts, but we don't really know that yet. Then we unplugged this end of this resistor. So now we no longer have the V offset over RC term, but we still have the Ibias over C term. And then we measured that Ibias over C term to be 25 millivolts per second. That corresponds to an Ibias value of 25 nanoamps. And then also you say, well, 25 millivolts per second is so much smaller. What is that? That's it's about 1% roughly. I mean, it's 2 orders of magnitude smaller than 3.2 volts per second. So I guess that tells us that indeed we have V offset is like about 3 millivolts. Okay, so we think we've determined Ibias about 25 nanoamps and V offset about 3 millivolts by looking at this opamp integrator. So it's kind of fun to extract those numbers that way. And you can see the math on page 6. I worked it out. And then it also shows you that an op-amp integrator is an example of a circuit where you have to be pretty careful about controlling these things. And the way you control it, so you can buy better op-amps that have a relatively small V offset, but even then you usually trim V offset carefully with this little trim pot that I'm going to show you how to use in just a minute. And then If you buy an op-amp that has field effect transistor inputs instead of bipolar junction transistor inputs, it usually has a much smaller I bias, so then the I bias effect becomes negligible. So you buy a better op-amp that gets rid of the I bias effect, and then you can adjust to trim out V offset. That gets rid of that problem. Okay, let's figure out what the next question is in the lab. Okay, now we're going to see how to actually adjust with the little potentiometer V offset. So we're going to take a 10 kilo ohm potentiometer. So 10 kilo ohm potentiometer. Okay, and the wiper. Oh, okay. So actually, here, let me write this here. So 10 kilo ohm potentiometer, and the wiper is the thing that you turn back and forth by turning the screw of the potentiometer. This is going to go to minus 9 volts. The instructions say minus 15 volts, but the lowest we have on our, it's basically the negative power supply, so minus 9 volts. Okay. And then one end of this goes to pin 1, and one end of this goes to pin 5 on your op-amp. So those two mysterious pins that you haven't been using until now. So we will wire those up, and then by turning this little screw back and forth like this, you can basically zero out V offset. So we will see that in just a second. Let me just wire it up for you. So I have now reconnected my, okay, well, first of all, I reconnected this little black wire, so my resistor over here is now grounded again. Okay, so now we have the V offset effect, the V offset over RC effect over here. And then I've connected, so the two ends of this trim pot, this potentiometer, one end goes to pin 1. I hope I plugged it into pin, yeah, here we go, right. One end is this little blue wire going to pin 1, and then that's the left end of the potentiometer. The right end of the potentiometer is this other blue wire, here, this blue wire, going to pin 5. And then the middle of the potentiometer is this red wire going to minus 9 volts. And then what you will see, so then, by the way, let's just see, I'll zero this, and you can see we have the kind of few volts per second slope. Okay. So then what I want to do is, I'll do that again, and let me see if I can turn this to change that slope. Oh, I made it worse. Oh, now I made it the wrong sign. Okay, now it's back. Okay, and then I want to turn it until it stays put. It doesn't have to stay put at 0, because we can zero it by pushing the button, but you want to flatten it out. So there we go. So I turned it until now I've pretty much zeroed V offset. Yeah, pretty well. I've pretty well zeroed V offset. And then I can push the button, let go of the button, and now, of course, now the thing is I still have the I bias effect, so I might have been off by like 1% or so in how much I zeroed V offset, because I might have overcompensated a little bit to take out the I bias effect. But remember, we saw that the I bias effect was like about 1%, like 2 orders of magnitude smaller than the V offset effect. So this is pretty much just zeroing V offset. So that's a useful trick to know. And then, by the way, here, let me just wrap up this section. So in real life, you would use a modern op-amp having far superior V offset and I bias specifications. For precision applications, there are also chopper stabilized op-amps that automatically adjust their own offset nulls. Having observed these imperfections and trimmed an op-amp's V offset by hand once, you will be aware of these issues if someday you need to select an op-amp for your own project. Okay, and then one last thing. So just be aware, here is the lab10 PDF handout, and then if we go to page 6, then you see, you don't necessarily have to follow all this, but you see here's my analysis for part 1. So like you may or may not want to scrutinize it, but I put in Ibias, and then I put in the offset, and I work out the rate of change of so dV out dt is V offset over RC plus I bias over C. And again, if you let the resistor's ground connection float, that was like where we unplugged this guy, it's basically like setting R to infinity, so then you only have the I bias over C term. Okay.